Hello, my name is Xin. Today I'm gonna present my work during the Data Science Seminar in Eindhoven University of Technology. The name of the project is TINC Library Extension for Stream Temporal Graph Analytics. The work is co-supervised by Professor Mikle and George. Also, this work is a continuity of the work which was done by a last year master student, Uter. First, I will introduce the structure of this presentation. In the beginning, we will introduce the basic concepts behind this project. Then I will introduce the motivation and problem statement. Next, I will talk about the techniques or tools that I will use in this project. After this literature study, I also did a use case study to understand what the library can be used for. Then we can talk about the design of the library by generalizing these real-world use cases. In the next part, I will introduce the evaluation based on these use cases. In the end, I will summarize my contribution and introduce my future work. Since the TINC library is mainly designed for analyzing temporal graphs, we need to know the concept of temporal graph first. As we can see in the slide, the temporal graph is an extension of a graph, in which the edges are associated with time labels. There are mainly two types of temporal graph. The sequence graph above means the two edges are connected at time 1, 3, 6, 7, and 3, 8, 9 respectively. As for the interval graph below, it means the edge is connected during the time interval, for example from time 1 to 3. We can actually find out many new problems after adding the time labels to the edges in graph. For example, we can compute the fastest path earliest arrival time from vertex A to vertex B. So, the last year master student Uter decided to develop a library TINC, which can help analyze these temporal graph related problems. The TINC library is built based on the DataCite API of Apache Flink, which is actually for batch processing. Uter really did a nice work and contributed to Apache Flink's open source community. Being inspired by Uter's work on TINC library, we find the research of temporal graphs is attracting interest from both academic and industrial communities. So I decided to continue with Uter's work. As the TINC library only implemented the batch processing part, I think it will also be interesting to extend it to support stream processing, which is actually more common in real world. So the problem statement is that we need to design and implement an extension of TINC library. The extension will be built on top of Apache Flink's stream processing API and do support stream stream temporal graph analytics. After defining the problem, we need to first compare the difference between batch and stream graph processing. For batch processing, we are analyzing static graphs, but it will be dynamic graphs in stream processing. The most important difference is that we need to do full computations in batch processing. However, this is impossible in stream processing, because we already start the analytics before we collect all the data. We can only do approximate computations in stream processing. For stream graph processing, there are mainly two methods. One is the graph stream, which is a representation of a data stream of edges. The edges can have state and support property streams, transformations, and aggregations. In my work, I didn't use the graph stream. I used graph window to extend the library. The graph window just simply slices the stream graph into a series of static graphs with timestamp. Then we can easily reuse the TINC interface to analyze these static graphs. Since we decide to abstract the stream graph as graph window, we need to find a strategy to slice the stream graph. Apache Flink's Data Stream API already provides a powerful functionality which can help us define various types of stream windows. As shown in Figure 3, There are mainly three types of stream window. For session window, the length of gap between each window is random or user-defined. For count window, the window will group a static number of raw data into one window. As for the time window, it will group the raw data based on time. There are also two kinds of window for count window and time window. There are tubular window and sliding window. For tubular window, it will just jump from one window to another, but the sliding window will slide on the data stream smoothly. In Wouter's work, the batch processing API can simply load historical dataset from disk files. However, it will be different in stream processing, because the stream data always come in pipeline, and if we cannot process it timely, the whole system will soon break down because of the congestion. So in order to benchmark the extended library, we decide to use Apache Kafka as the message feed, which can help us smooth the incoming data stream. In stream processing, the incoming data stream is always very huge, so we cannot simply deploy the stream processing task on one computing node. We need to deploy the task on a cluster of computing resources. In our work, since we need to benchmark the performance of the extended library, we decide to use Docker to manage and configure the cluster. Docker is a lightweight software layer virtualization, and the network throughput between Docker's containers is extremely high, which is very important for our task, because the computing nodes in the cluster need to communicate with each other frequently. After introducing the techniques and tools, we can then go to the use case study. We try to figure out three common real-world problems. The first one is about the traveling by plane. If we want to fly from airport A to B with the fastest path and earliest arrival time, we can then use the temporal graph algorithms. In Wouter's work, he analyzed the flight info based on historical data, but in real case we are not able to obtain all the information. For example, we cannot know which flight will be delayed if it hasn't departed. So we need to make a decision based on the real-time data. We can define the use case in this way. The flight map is abstracted as a temporal graph. Find out the shortest path with earliest arrival time or fastest path between airport A and airport B. Make optimal decision based on the existing stream data. The stream data is updating periodically. In the second use case, we still focus on the path optimization problem, but we change to the road traffic. Figure 6 is a Dutch road map. We can treat the crossings as vertices and roads as edges. Again, if we want to find out the earliest time to arrive another place, we can collect and analyze the real-time traffic information. However, the difference is that, unlike the periodically updated flight information, there will be massive traffic data generated per second. So we need to recommend the newest optimized route to the users based on the continuously updated data stream. In the third use case, we will discuss about a social network. In social network, the people can actually be treated as vertices, and they are connected when they are chatting with each other. Again, we can represent the social network with temporal graph. In Wouter's work, he tried to figure out the most important vertex in a social network, but the analytics is based on a complete historical dataset. Actually, we can also analyze it in a streaming manner, because if we consider all the historical data, all the people are somehow connected with each other. The result cannot reflect the importance of a vertex at a specific time. If one people in the social network is very active in the beginning but keeps silence later, the analytics based on all historical data will not able to figure it out. So, after the use case study, we can design the extended part of the library based on these use cases. First, we need to follow the design requirements proposed by Wouter, like ease to use or good documentation. But for the extended part, I think there are three other requirements. They are unified interface design, use case-oriented generic methods, and further extension support. The interface is designed as shown in listing 1. The user can simply use it by setting a few parameters. In order to design a generic library, we try to summarize the similarities and differences between these use cases. We mainly find 3 common aspects of these use cases. First, we cannot wait until we collect all the temporal graph data. We need to give timely analytics results based on the collected stream data. The stream temporal graph data can be modeled as several slices of graph window. We can then divide the stream analytics task into several batch processing tasks. We don't care about the global optimum solution or result. We are interested with obtaining a series of local optimum solutions or results. As for the difference, the most important difference is that they need to slice the stream graph with different window strategies. So the key requirement of the design is that the user can choose the stream window according to their own use case. After implementing the library, we also evaluate the performance of the extended APIs. The library is mainly evaluated considering throughput, latency, and result comparison. Figure 8 shows the throughput evaluation of second use case. In second use case, we crawl the flight information from several European airports websites. We can find that the performance is getting better when the number of nodes goes from 1 to 4, but it's getting worse after that. The possible reason is that there are 4 processor cores in our test laptop, so they will compete for resources if the number of nodes is more than the number of processor cores. But in general, the throughput is not changing a lot with different number of nodes. Figure 9 shows the latency evaluation of the same use case. We can find that the performance is getting worse and worse when there are more nodes added to the cluster. After analyzing the codes, we find 2 possible reasons. The first reason is that we actually didn't fully take the advantage of Apache Flink's data stream API. We just sliced the stream graph into several graph windows. The throughput can be improved with more nodes to receive more data. However, the cost for synchronizing and replicating is also getting larger, which will lead to higher latency in the cluster. The second possible reason is that we didn't configure the cluster properly. As we are using Apache Kafka as the data producer, there should be a balance between the number of Kafka nodes and the number of Flink nodes. Otherwise, the performance will be bad. For use case 1 and 3, as the incoming data stream is not continuously generated, we cannot use it to benchmark the throughput and latency. And actually, we simulate the data by ourselves. In this case, it's interesting to compare the real-time results with results based on all historical data. In use case 1, the query result based on all historical data remains the same as those generated during stream processing. For example, if we want to fly from Paris to Amsterdam, in the stream processing version, the system just tells us you can choose this flight, and it will just output the result continuously to the screen. And in the end, we will also analyze all the incoming stream data and give a result. So in this case, the result is the same. As for use case 3, the most important vertex in social network changes frequently as time changes. We use it in use case 3. We use it to test the temporal betweenness and closeness algorithm, we find the most important vertex in graph is changing over time, because the temporal graph is changing a lot as people start and end chanting randomly in the social network. Actually, the dynamic result seems more interesting and useful. We can know the most important people at a specific time. Otherwise, the result over a historical dataset could either overestimate or underestimate the importance of some vertices. It cannot reflect the dynamic change if one people is very active in the beginning and keeps silence after that. Overall, we think the performance of the extended API is acceptable while running a single node, but considering an even larger incoming data stream, we cannot greatly improve the performance by running a larger cluster. As we have discussed before, the major cause is that we decide to use graph window to extend the library. There is a bottleneck while transferring data stream to dataset. Also, we cannot fully make use of the distributed miner of DataStream API. Although the design has some bottlenecks facing massive incoming stream data, it can still be used for first and third use cases. Because the incoming data stream is periodically or randomly generated, and there will be much less congestion in this case. Actually, there is also another option in practical application. We can just give up the data that we cannot handle. Although the accuracy of the result is reduced, we can make sure the stream processing system still works well instead of breaking down. In the end, I will summarize the contributions in this work. First, I extend the Think library to support stream temporal graph analytics. Secondly, I did some use case studies to design the generic method. Thirdly, we benchmarked the extended library with 3 use cases. And in the end, we discuss and analyze the benchmark results. As for the future work, there are a lot of things to do in the future. First, we may implement a streaming version of Jelly library which can be called as Jelly Streaming, and it will be good to use it to implement the graph stream. Also, we can implement more graph algorithms, especially stream graph algorithms. And also, we are interested with combining the historical data and stream data because currently we only use the stream data in stream processing API, and we only use the historical data in batch processing API. And the last thing is we need to improve the performance of the library. So that's all. Thank you for your listening.